So our differential equation is dy dt equals y squared minus a squared. Again, a is a constant. You could pretend it's 1, you could pretend it's 2. I mean, if a is 2, this would be subtracting 4, of course, because you're subtracting a squared. I made it an a squared instead of just a plain a, so we didn't have to bother with square roots when we factor it. Generic initial value problem, y of 0 equals y sub 0, or again, if you don't want to call this y naught, you can. Separate variables, integrate, try to solve for y. To integrate the right is always, or almost always easy, it seems. You would just get t plus a constant. Integrating the left is typically the harder thing to do. And I told you want to use partial fractions here. So you'd want to write this fraction 1 over y minus a times y plus a as some constant over y minus a plus some other constant over y plus a. Then you want to solve for capital A and capital B. Since you don't know what little a is, most likely capital A and capital B depend on little a, and they do. The trick is to multiply both sides of this equation first by the common denominator y minus a times y plus a to get complete cancellation on the left to make it be a 1. And partial cancellation on the right. Y minus a times y plus a times that term makes the y minus a's cancel. And you're left with a y plus a on top. And y minus a times y plus a times that term makes the y plus a's cancel, leaving you with the y minus a. Now you can expand this and set coefficients of like terms equal to each other, but it's quicker just to pick some special values of y, like a and negative a. If you replace y with a, this term becomes 0. The b goes away. And you're left with 1 equals 2 times little a times capital A. So capital A is 1 over 2 times little a. I am implicitly assuming a is non-zero when I write this. When y equals negative a, this term goes away. Negative a plus a is 0. And you're left with 1 equals b times negative 2a. That's what I have here. Solve for b. Again, assuming little a is non-zero. Again, the little a could be positive or negative. It's maybe simpler to assume it's positive. So I said, so let's say little a is positive, just for simplicity in your mind. To integrate the left-hand side, ultimately, do you want to go back to the integral? You need to integrate this plus the integral of that. The constants can be brought out in front. You're going to get logarithms. I included the absolute values initially, but we will ultimately get rid of the absolute values. I also included the integral of the right-hand side here for completeness. And now just solve for y. Easier said than done, right? You experienced it. You do want to use properties of logarithms to help you solve for y before you exponentiate. You'd want to bring these coefficients up into the powers. That's a property of logarithms. And then you'd have the difference of 2 logs. That's the log of the quotient. So that means you're going to get this kind of thing right there. Again, I could have gotten rid of the absolute value signs at that point. I didn't yet. Remember, always remind yourself what the goal is. The goal is to solve for y. So we need to get rid of that logarithm. So exponentiate. E and that logarithm will cancel. E to the x and natural log of x are inverse functions. So you're just left with what's inside. I got rid of the absolute value signs there. And over here, I use the fact that there's a property of exponents that says this. And e to the c1 I called c2, or effectively plus or minus c2, if I allow c2 to be negative. That exponent 1 over 2a is not so nice looking. Well, just raise both sides to the 2a power. That gets rid of the 1 over 2a there. E to the t to the 2a power, e to the t to the 2a power becomes that. You can multiply those exponents. And the c effectively here is c2 to the 2a. The c is c2 to the 2a power. Now solve for y. Here are the details. There's solve for y. There's a general solution right there. You got that? If you got that, good. You've made it most of the way. And then again, I have this generic initial value problem where I don't say what y sub 0 is. I just pretend it's something specific. And to find the final answer, I need to figure out how c depends on y0. And here's how c depends on y0. And then you can substitute that in for c in these two spots. And then you've got fractions within fractions, and so that would be good to simplify as well. And where's my final simplified answer? There, I plugged them in. And so that's fractions within fractions. I don't like that so much. So then I multiplied the top and the bottom of this by the common denominator that you see here, y0 plus a, and wrote my final answer like this. I am using the phi notation here because we're going to start doing that more often. The phi is just the function name for your solution. I made the y0, the initial condition, a subscript. I will start doing that more often as well. It is a function of t. A and y0 are fixed. It's a complicated function of t. So it can be done, yay. But boy, it wasn't easy. So many places to make a mistake. I'm fortunate that I did not make a mistake. Okay, that was fortunate. It's easier to think about it qualitatively. It's easier to think about the slope field. Let's do that next. If you want to finish copying down what I have here, I am recording this for one thing, but I also you can come up after class and I can show you the piece of paper here. Let's think about it qualitatively. dy dt equals y squared minus a squared. It's an autonomous equation. The right-hand side only depends on y, not t. But maybe, it also depends on a. Maybe I should make the a be a subscript of the f. Question is, what does the slope field look like? That's what I'm after. Like we emphasized a little bit in class, I don't know, last Friday or something. It's good to graph this right-hand side function first, where y is horizontal, before you graph the slope field. Before you graph the slope field. How do you do that? Well, that's a parabola, right? Opening upward, quadratic. Its roots are plus or minus a. A is positive, then a would be, say, right there. And its opposite, negative a, would be over there. This is going to have a vertical intercept when y is 0 of negative a squared. Maybe that's down here. The graph is going to look like this. That's the graph of f sub a of y. And changing a would just shift this graph up or down, wouldn't it? As long as a is positive, you're going to have two intercepts there. And what does what do those intercepts correspond to in the slope field? What are they called? Certain kind of solutions. Equilibrium solutions. And they're horizontal here in the slope field. This is y equals a here and y equals negative a here. Those are constant functions that solve the differential equation. Wait a minute, I didn't see any constant functions in the answer, did I? Well, if you replace y sub 0 with a, those terms go away. You get zeros, and you're left with a constant. In fact, you're left with a constant ultimately equal to a, I think, yeah, because you get cancellation there too. And if y0 equals negative a, these go away, and you're left with this, and you get cancellation as well, and it simplifies, I believe, to negative a. This is capturing the two equilibrium solutions if you set y0 equal to a or negative a. What about other solutions? If y is bigger than a, the right-hand side function has positive outputs, the slopes of solutions are positive. You need positive slopes up here. And evidently they get bigger and bigger as you move further away from a. You need positive slopes down here too, because over here the function output is positive. When y is between negative a and a, you have negative outputs for the right-hand side functions, so the slope field has negative slopes. Most negative at y equals 0. Solutions follow the slope field. So besides these two equilibrium solutions, other solutions look like this, and they're horizontal translations of each other for autonomous systems, not vertical translations. That test question was false. Like that. In lecture 9a, I relate this to something called a phase line. This is the phase plane, you might say. Slope field. I relate this to something called a phase line, a very important topic in lecture 9a. Did I clarify anything? Not saying this is easy, but it's amazingly, it's doable. But this is easier. Mathematica does solve the differential equation as well, by the way. Though with D-solve value, it gives you an answer that involves tanh and arctangent. Yes, that H is no typo. It's called hyperbolic tangent and inverse hyperbolic tangent. Why does it look different than our answer? Here's our answer. And by the way, I did double check our answer in Mathematica by actually differentiating it like this, and also squaring it and subtracting a squared. These two things simplify to the same thing. So why is this in here? Well, I didn't double check that it's equal to ours, but it should be evidently. How, you might wonder. I will tell you that hyperbolic tangent is actually an exponential function in disguise. Inverse hyperbolic tangent is actually a logarithm in disguise, and you might wonder, well, I see some exponential functions in here, but I don't see any logarithms. Somehow it must simplify to the same thing. I haven't double checked how. Maybe you've never heard of hyperbolic functions before. They are related to exponential functions. Why do we call them sinh and cosh and tanh? Hyperbolic sine, hyperbolic cosine, hyperbolic tangent. Because they're actually related to trig functions, amazingly. If you use complex numbers involving imaginary numbers. Amazingly, they're related to each other.